We'll start with who we are. Some of you may know who we are, some of you may not. And so for those of you who don't know who we are, we're a team of agronomists, consultants, people who work with farmers spread out across the United States from New York to Washington, down to California, Florida. We're working with some global projects, working with all kinds of different crops, ranging from corn and soybeans to cherries and apples and vegetables. Part of that team is also a manufacturing team in Ohio, where we manufacture some plant nutritional supplements. We don't do anything with the commodity fertilizers, but we do have some products that we manufacture there in Ohio. So that's who we are. And we're known for looking at challenges and helping farmers solve challenges, which is the reason we're here today. We hear that some farmers are interested in looking at what the challenges are and how we can fix them. And one of the things that we do very differently than many people is looking at the reason why we have the challenge. We go to the root. Instead of just looking at the symptom, we want to know why is the symptom there. If you have a headache, it's probably caused for some reason. So we're very passionate about growing healthy plants. We believe that healthy plants will produce healthy soil, and when you have a healthy soil, you can grow healthier plants. And so we focus on growing plants that are healthy, and John will be talking more about that. So I'd like to introduce the rest of the team that we have here with us. John Kempf is the founder of Advancing Eco-Agriculture and an amazing young man. And I will let John, when he talks, I will let him share how he got started and what has driven him to this point and how we have come to understand the things that we have and are pursuing. And then we have Jason Stoll, he's a customer service representative in Bloomington, Indiana. And so if you call the 800 number, you'll probably talk to Jason, and he will either answer your question or connect you with the person who has the answer for it. And then my son Josiah isn't on the AEA team yet, but he's here with us. And
keyword being yet.
Yet. Yeah, keyword being yet. Often when we get home from meetings like this, he'll do a presentation, afterwards. And then I'd also, most of you probably know Brad Koehn. He has been working with us as a farmer and is also working with us as a point of distribution out here. So Brad has been a vital part in what's happened here in Kansas. So for today, our goal for today is to look at what the challenges are. There's all kinds of challenges that we all face regardless of what industry we're in. And in farming, there's many challenges, and some of those we can't control, like weather variabilities and weather extremes. There's challenges of intensifying pest pressure. One of the things that we've heard a lot working with Ashley, working with Brad, is spider mites. What about this? And this picture is just a clip, and I don't know how plain you can see it, but that's giant ragweed. That green stuff is tall as the combine. and that's the thing that was at the bottom. There's, maybe you can't even read it, but it's basically saying that there's a lot of weeds that have become resistant to herbicides. Weeds are continuing to become more and more challenging. One of the challenges that we often see on farms is compaction. Is that most of the farms I've been on, that's been
it's a way bigger problem than people realize.
Yeah, I was just on a farm last night over Garden City area, and it was sand. We took the shovel, 4 or 5 inches down, we hit a hard pan, and then I was digging across, and I was able to find the ridges where either they had a disc or something in there, and the ridges were in, and this was probably 2 or 3 years prior, or 2 or 3 years ago, because this farmer hadn't done anything. So compaction's a challenge. Soil fertility. How many of you look at your soil samples and you see lots of soil fertility, P and K, but you look at tissue samples or whatever and it seems like it's not there, or you put on a lot of nitrogen or potassium. I've heard that a couple of times. Put on a bunch of manure and my soil sample's the potassium's not moving up. This slide is really what got me started on this whole journey 6 years ago, is to realize that 1950 to 1999, and this is USDA data, we've really dropped in a lot of crops or foods that we eat. 50% decrease in calcium on tomatoes. It's just, that whole thing is what actually got me started thinking that we need to eat. The presenter that was talking about this said we need to eat 3 apples to get the same nutrition our great-grandparents got from 1. And somehow that sparked within me. I was like, that's going to be a problem. My great-grandchildren will need to eat a bushel of apples to get the same nutrition I got from 3 apples, which is the same nutrition my great-grandparents got from 1, and they'll be eating all the time, which is the problem. So we have a lot of challenges, and we like to take those challenges and turn them into opportunities. In every challenge, there's an opportunity. And what we focus on doing is building, regenerating the soil, building that soil carbon back up, building that organic matter back up in various different ways, and really focusing on the soil biology. And when we do those things, we focus on quality, great things start happening. And so I've asked Brad, who was the first farmer out here, what is that, 4 years ago now? Brad called me out and we had a long conversation, and things got started on a small scale, and he's been doing it all these years now, kind of growing into it. So we've got a couple slides here that Brad's going to talk about, just to give you all an idea of what he has seen with the regenerative model of agriculture.
Well, good morning, everyone. Yeah, I started it 4 years ago with a failure in garbanzo beans, which I think all of you don't know or haven't seen probably a garbanzo plant. But if you have, it's hummus. They make hummus out of. And I was looking at a plant that I could raise with low water. And I overwatered it. I watered it like corn. And so we had a failure the first year. And also in our organic acres, we planted a lot of acres behind our failed wheat, 2 garbanzo beans, and they did not come up. So we have pythium in our soil that took after the disease, and didn't make them come up. So then at the quest, I would look forward, and that's why I called David, and we started talking about, hey, let's raise garbanzos next year, let's make it a success. So we took sap samples on a half circle of garbanzo beans and looked at the mineral deficiencies, what the garbanzos needed, come up with a plan, and we sprayed on them and put on a little nitrogen, put on some foliar product, I forget what those products were, put on, and they quit nodulating, but they renodulated, and those garbanzo beans made 45 bushels to the acre, which is good for a garbanzo bean crop. So I felt like that was a pretty good success. And then we moved into 2015, and I said, David, we have got a circle of organic. Go back a little bit here, that garbanzo beans were not organic, they were commercial. I have durum wheat that froze out. I want to plant organic corn. What do we do to this corn to raise good crop organically? So we came up with the plan. We put out what we've always used, compost in our area. We put some gypsum out there. We put a half a ton of humus, which we had made with Edwin Blotter's technique of making humus more carbon in the manure and building humus. So then we raised the crop of oat and peas before the cover crop. Add the cover crop. We put on Spectrum, Rejuvenate, and Sea Shield, which is a fall primer. But I did it in the spring on the cover crop because it was later in the season. And we bit down the cover crop and we planted corn. And this is the corn crop that came out of that. I think it was the year we had a lot of rain and we planted it later, is that correct? So the corn was put in 1st of June. We rotary hoed it once, we cultivated it twice, but there was hardly any weeds. The year before was durum wheat, and we had to swath it down because the weeds were so bad. To kind of give you an overview of what, yeah, we had weed seeds in the soil, but with the cover crop, with biology working, it changed the soil to where it made it more balanced, per se, and the weed pressure was minimal. I spent $30 an acre in roguing because I was particular. I did not want any weeds in the field. So they went through the field and just pulled weeds out here and there. It wasn't solid by any means. We harvested this corn in November. It was 19 moisture because of planting it late because of the wet season that we had. May 215. In the course of the season, I was putting on nutrition through the foliar applications, through the pivot, fertigation, and I put in sea shield, some phosphorus, and some other products. I did not know there were spider mites out there. My agronomist called me the next day and he said, "What did you put out there? You're killing the spider mites." Well, I said, "I'm just fertigating. And I'm not doing anything different. I'm just putting on nutrition." Well, and he said, "Well, they're dying." Well, that's interesting. So as we went on longer into the season, they did not come back. He said, "Our next challenge is going to be corn borer and earworm." And we did not have issues with that either. As you see, there's the corn crop before we harvested it. Now, is this year's corn?
Yeah. That's the pictures you sent me.
Kind of blurry. Anyway, I was impressed with that, so that's what the one circle of organic corn. So I asked David, I said, "Okay, can I plant 2 years in a row of organic corn?" Well, he said, "Yeah, you can, no problem." So we did another year. We still did not have spider mite or corn borer issues. It made 220 last year. I said, "David, I still want to go another year." With the organic market, it's good. The certifiers will say it's kind of a gray area to go the 3rd year, but we'll go a 3rd year. We're going to take that risk. Between every crop of corn here, we did a cover crop of oats and peas. Good for diversity out there, keep the biology alive, change our soil structure, weed pressure. So this is actually a picture of our corn crop this year. It's the 3rd year in a row of organic corn. No synthetic fertilizers applied. No nitrogen applied. Other than I've had 3 tons of compost, or conditioned manure, what I call it, on this field. And so I do not know what the yield potential is here, but it looks just as good, if not better, than last year. I have not counted the years, or it's at that 32,000 population.
Any mite pressure up there this year, Brad?
What that?
Any mite pressure, spider mite?
No, I just looked at my report from Woodrow a little bit ago, and I do not have spider mite pressure in its field.
What about in your area up there in northern Kansas? Was it a summer for mites or?
We did not have it much this year. I did spray some other commercial fields with 4 spider mite, and took care of it. There's been spider mite in other areas around us, but it's not been a spider mite year in our area. But they're there, there's some of it there. This is actually a field of dryland corn that I have out. That's organic. Is that correct?
I think
Yeah.
those pictures.
Looked like it to me anyway. That I just did the biology and spectrum and rejuvenate after the corn was up. Rotary hoed it once, cultivated it once. The field is pretty clean. I don't know what happened here, but it doesn't look bad at all. We'll see what it makes. We'll go back here. I've got about $50 an acre in fertility in its organic corn of AEA product and biology. This here is a local farmer that's using the program. It's organic. That side is a half a circle that was this year, the first year on the AEA program. It's more compacted soil. He's got more spider mite. He put 10 ton of manure on, 8 ton of manure on that half because he wanted to build up his soil. This other side is second year of AEA program. It's darker soil, more root, and 2 years per plant, and no spider mite. They're side by side on the same circle. Anybody have any questions?
I've got one question for you, just minor thing on, just so I understand on the organic part of things. If I understand right, is there a restriction in organics, like marketing a crop in the same year you put raw manure on, whereas there's not a restriction with composted manure?
There's not really a restriction on raw manure as far as I know. Or compost. The only restriction that you would have is if the feed yard, you'd have to get a statement from the feed yard that they're not putting any fly spray or commercial application of fly spray on their manure to kill the flies. That's the only thing.
State to state too, Brad, on manure. If it's composted, there's less restrictions than if it's raw. And then there's also a restriction on anything that's a ground fruit like cantaloupes, or if it's potatoes or anything in ground, there's a number of days that you cannot apply manure before harvest. And that changes from state to state. But as long as it's composted, I think the restrictions are lifted.
Okay, that puts it in context for me, for what I heard, okay.
Who's your certifier, Brad?
GOA out of Ohio.
Betty?
Yeah,
Okay,
yeah,
she's a good girl.
yeah. I don't know if anybody met Dennis Warnicki from Tiny O. He's behind the company that makes the biology, so he's with us here today.
Sorry, Dennis, I missed you. That's all right.
Also, with the conditioned manure, why we do it that way, or the compost, is that we get it up to heat, so we don't have to put more weed seeds out on the plant. On the field, and we break it down for more availability. So, anything else?
How do you apply your compost?
With that?
How do you apply it?
With the compost? Get the ice butter box.
Just broadcast?
Yeah.
Brad, how many tons did you reduce your application from going from the raw manure to your processed manure?
What we've been doing for quite a few years is 5 tons. of conditioned manure.
5 ton versus how many were you have just raw?
Probably 20, but that's been backed off also because of the oversaturating the soils
Right.
and water usage. I think a lot of guys are putting 10 on. We're backing down to 3 already. Some guys are doing 2. The nutrient, if you get a nutrient test, it's the same with raw as it is with conditioned manure. Other than when we add the biology to it, we add biology to our compost also. And that actually gives us a little bit more phosphorus and potassium. Our nitrogen pretty well stays the same. Of 30, it's actually 30, 45, 45.
Are you guys producing the biology also?
Yes.
What do you got for biology? What facilities and monos or what?
And actually a whole array of beneficials within our biology, depending on which products you're using. There could be as much as 35 to 40 strains within the product.
And so he's using Tanio's products, and I'm familiar with Tanio's. For $50, you're producing 215 to 220 bushel of corn, organic. That's phenomenal.
That's without.
Well, let's back up a little bit. That dryland field, I put $50, that was compost history. I did not put that on this year. I just did the foliar through AA at $50 on that.
That's still phenomenal. I mean, plus the price of organic corn. And I wonder why. I mean, I produce an organic product too, but, it's phenomenal what they've done.
Well, and one of the keys to that is not only the biology, but the full package
Sure.
program. Paying attention to plant sap analysis and nutrition and all those things come together as a package.
And that's what we've seen in the organic industry is, it is sustainable where with conventional products, the NPK program has long been proven unsustainable. You're talking about your hard soils. I mean, when we're irrigating, what are we putting on the soil? Calcium carbonate. They use it in cement. I mean, all we're doing is making our soils harder. Well, we gotta have biology in there. We gotta have humus in there. I've said for a long time we're missing the humic acid fraction in it, and that's what we're doing. If we could get organic soil or organic matter up to 5, which is unheard of out here, okay?
It is.
I mean, I asked Dan Oak and Dana Dines when they did the humic acid test back in Iowa the last 3 years, and I asked Dan at Acres last year in Omaha, I said, how come you did it in Iowa with organic matter of 5%? Why didn't you come out to southwest Kansas or south central Nebraska where we have organic matters of 2 or less, And he said, yeah, we screwed up, Steve. And I said, well, come on out anytime you want. So he is, but it'll be interesting to talk to him this year in Columbus. But, you're proving what we've seen for a long time, that why aren't more people moving towards that organic side? I mean, yeah, it's you got that conversion, it costs money, but yet you're showing that with minimal input. You guys are showing an ROI that's phenomenal. I got a friend of mine up in south central Nebraska that's been organic for 20 years now. And Rex is seeing, he started out with 75 to 100 bushel corn, but with the biological approach, and now he's doing the same thing that you guys are seeing. I think it's phenomenal.
I'll back up a little bit too. You brought up the organic matter. That first year of corn, I took a soil sample, it was like 2%. The next year, I took a soil sample again, 2.8 in 1 year's time. And it pretty well stayed there. I wonder if my last one was 3.2. John will explain more here today, and we'll just
What kind of
fun
peas
day
did
here.
you grow? Were they just field peas or cow peas, or what were you using?
They were just cowpeas they were just in the mix.
Okay.
You plant cover crop on your dry land?
What's that?
You plant cover crop on your dry land?
I did not. That's
Yeah.
where my fine line, that's where I need to grow into, I have to step into it, I
That's
guess.
a paradigm shift.
Thank you, Brad. So, we can see how when we work with the soil, when we work with biology, things happen. And so it's one of the things I think is important to understand is that we're not about a magic product, a magic bullet. It's like Dennis said, it's about the whole system. It's about the way we manage our crops. So we've talked about the challenges, the insects, the diseases, the weed pressure. Brad has shared what he has seen, and so we want to spend the next however much time we have before lunch John's going to talk about why are we seeing, or why we believe that all these insect pressures are increasing. Why are the diseases mounting? Why is weed pressure, why are they becoming more resistant? You know, it seems like it's on a downward spiral, as Max Burney put it when we met with him. It seems like the last 3 years, it's not going in the right direction. That's what it feels like, and that's what Brad told me 5 years or 4 years ago in our first conversation. He said, something's wrong. I've got all these traits in my corn, and I'm still using the same amount or more of my fungicides. Something's wrong. And so that's why Brad has, wet his feet and been very successful. So, John, tell us why and how, and feel free to ask questions, even about how John might have come here.
All right. Well, good morning, friends. It's an honor to be here. We have an hour and 15 minutes between now and lunch. And Brad and David have asked me to talk about things that I normally talk about in 3 hours. So I've been listening to the conversation this morning. David asked you the question about what are the major diseases, major insect problems. And there's many different pieces that I could talk about, that I would love to talk about, but we don't have time to fully do some of these topics justice. I'm going to do the best that I can, make them as simple as possible, and I'm also going to be speaking very rapidly and very quickly. I'm not from Kansas. I don't speak quite as slowly as Brad does. I'm going to speed it up a little bit. My own background is that of growing up on a family fruit and vegetable farm in northeast Ohio, about 20 miles south of Lake Erie. So we're in the snow belt off of Lake Erie, which means that we get about 90 inches of snowfall every winter, and our summers we get an average of about 40 inches of rainfall and very humid conditions, which is the perfect environment, a petri dish for disease and insect problems on the fruit and vegetable crops that we were growing. So we were very mainstream growers, using very intense pesticide applications. My dad was the pesticide distributor for the local region. I was a licensed pesticide applicator when I was 16 years old. And as a result of Dad being the distributor, we were the first people to always try the newest, latest, and greatest insecticides and fungicides that were released onto the marketplace. And at this point, we started growing vegetables in 1994, and fresh market vegetables, our crop mix kind of evolved and changed over the years. In the early 2000s, we were growing 4 crops that represented about 70% of our planted acreage. Those 4 crops were cantaloupe, zucchini, cucumbers, and tomatoes. Those 4 crops were about 70% of the acres that we were planting. We had a 3-year period, 2002, 3, and 4, 3 years in a row, where we had a variety of different weather stress, severe rainfall, different times of the growing season, and we were unsuccessful, completely unsuccessful at managing diseases and managing insects using pesticides. We could not get control of powdery mildew. We couldn't get control of downy mildew. We couldn't get control of bacterial speck and bacterial spot and early blight and late blight. 3 years in a row, we lost more than 70% of each of those 4 crops to a variety of different diseases and insects. So we were stressed economically on the farm, stressed emotionally, and we had a lot of incentives to try to understand what was happening and see if there were better ways of figuring this out. But then kind of the real light bulb moment happened in 2004. So 2004 was the third year of this 3-year period. And in that year, we began renting a field from a neighboring farm that bordered right up against one of our own fields. So we used to be farming this one field, which was a very long, narrow strip, and we were tilling it and planting it up and down the slope because it was fairly narrow. And now we had the field right beside it. So we switched the direction that we were tilling and planting. We started planting crops directly across the field border. That year, we planted that field into cantaloupe, and it was right out beside the road where everybody could see it that was driving by. And at harvest time, on the old soil that we had been farming for the last decade, we had 80% of the leaves infected with powdery mildew. In spite of all of our fungicide applications, every 5 days we were out there with fungicides. 80% leaf infection with powdery mildew. On the new soil that we were farming that year for the first time, there was no powdery mildew. You couldn't find any. It was not like 5% or 10% leaf infection. It was 0. This was the exact same variety, had been planted the same day, had the same fertilizer applications, had the same fungicide applications, but we got 2 completely different results. That was kind of the real wake-up moment for me, is I wanted to know what are the differences between these 2 plants. What allows one plant to be resistant to powdery mildew when the next plant 2 feet away is susceptible? So I started doing a lot of studying, research, calling people, talking to people all over the country, all over the world for that matter, and developed a group of mentors who guided my studying and reading for the next several years. And over the next couple of years of very intense learning and applying what I was learning on the farm, I learned a lot about plant immune systems and the capacity of plants to be resistant to diseases and insects. And to simplify it all down very simply, almost an oversimplification, we understand that each of us have our own immune systems, but our immune systems don't all work equally well. All of us know friends who become ill with the first cold or flu bug that comes along, and then we know other people who practically never become ill. The only difference between those two is how well their immune system has been supported with nutrition over the course of their entire lifetime. In fact, from even before they were born. And the same concept also holds true of plants. Plants also have an immune system that is called an immune system that provides the same or similar mechanisms, and I can say with complete confidence, beyond any shadow of a doubt, that plants have the inherent capacity to be 100% resistant to diseases and 100% resistant to insects if they are supported with the right nutrition. That's a really big mouthful. That's a bold claim. That's a big statement to make, but we have seen the evidence of that today on thousands of farms. I'm not saying that based on wishful thinking or based on reading something in a book. What then happened from that experience on the farm, I eventually, by midsummer 2006, I founded Advancing Eco-Agriculture as a consulting company. We did consulting work only primarily on dairies and on fruit and vegetable farms for several years. And then eventually we got into product manufacturing out of frustration with the quality of products that were available in the marketplace at that point. And they've evolved a lot since then, but they still have a long ways to go. And today, flash forward to today, Advancing Eco-Agriculture is a company of about 25 people. In agricultural terms, we're a relatively small company. And what we have become known for is really 3 pieces. 1, disease and insect resistance on all types of crops. We have had this degree of success on fruits and vegetables, on nuts, on avocados, on macadamia nuts, on wheat, on corn, on soybeans, on rice. I mean, just at this point, the list of crops, the total list of crops that we've worked with in some way is 200 crops. Crops that we have in-depth knowledge and experience with is about 60 crops at this point. The reality is that when you begin understanding the underlying principles of disease resistance and insect resistance and how it works inside a plant, all plants are different and all plants are the same. Photosynthesis is the same in any plant. The same with the immune system. The immune system processes are the same in any plant. So I have complete confidence the things that we have learned in other areas and other places will work here equally as well as they will work anywhere else. So what brought me here today is and led to the formation of advancing eco-agriculture. In these early years, as I was working with growers as a consultant doing consulting work, the intention, the reason growers hired us and wanted to work with us was to help them grow crops that were disease and insect resistance. That was kind of the hook that we hung our hat on. But then, two other pieces happened as well. We learned two other things. The first was that when we grow plants that have an immune system, a functioning immune system, they have the capacity to transfer that immunity to the people who consume that food. So with blueberries, for example, blueberries are supposed to be really nutrient dense. They're really good for you. They enhance your immune system. Why? Because of the anthocyanin content. The anthocyanin concentrations of blueberries can really enhance your immune system, right? Well, in 1992, Michigan State University conducted some research where they compared extensive blueberry samples, and they discovered that the anthocyanin concentration in blueberries can vary by a factor of as much as 25x based on variety and environment. So 25 times higher anthocyanin content in healthier plants. That's a huge variable. It's a huge variable. So I realized that these same compounds that give a plant immunity also enhance our immune systems as well, and we can have a legitimate conversation about growing food as medicine. But the second piece was perhaps even more startling, which was when we observed, the first time we observed this was on a strawberry trial in California. We observed that it is possible for us to build soil organic matter while we are growing a crop. So within agriculture, we have had this paradigm, this perception that the process of planting a crop and harvesting a crop is somehow, by its very nature, inherently extractive, that we are extracting nutrients and extracting organic matter from the soil, and that we are depleting the soil in some way. And that can be true, and that is true if we manage in that way. But it doesn't need to be true. It is completely possible for us to grow a crop that is so vigorous and so healthy that we can actually build soil organic matter while we are growing a crop. And I don't know if I'll have time to do this conversation justice today. You heard Brad give a brief example where he's gained, in 3 years, he went from 2% organic matter to 3.2%. Growing corn. You can grow corn. In fact, corn is one of the best crops to build soil organic matter with. So that's a whole other topic that we'll talk about later today if we have the time and the opportunity. So then I looked at these three pieces. And these three pieces in combination say, wait a minute, we can grow plants that are resistant to diseases and insects, that are producing food that really is food as medicine, and we can regenerate soil health at the same time. This is something that is incredibly inspiring. I find it incredibly inspiring personally, and I became very passionate about seeing those models, these nutritional models, and these frameworks of how to manage plants become the mainstream, become the status quo. But I realized that I can't go talk to cherry growers in Washington and talk to strawberry growers in California and talk to corn and soybean growers in Kansas and have a conversation about building soil organic matter and growing food as medicine and growing disease and insect resistant plants, because with the exception of disease and insect resistance, for the most part, that is not what pays the bills. That's not what is going to inspire growers to change. And I realized that if I really am passionate about wanting to drive change, then we have to figure out how to accomplish these types of results successfully, repeatably, consistently, and there has to be a really strong economic motivator. The comments that you were just talking about earlier, what Brad has experienced, we are at one of the things that we obsess with at Advancing Eco-Agriculture is we want to make absolutely certain that every single time we work with a grower, there is a tremendous economic upside. Because when you have that, and you see an economic incentive to begin managing things differently, now you have the opportunity, the wherewithal, and it actually makes sense to try things and to try to work with them. So,
Can I say something in regard to that?
yes.
I've been doing ag consulting now since 1976. And I still don't see people, this plays right into what you're saying. There's, in my opinion, there's too much talk about my yield, you know, like, I'm getting 250 bushels per acre, I'm getting 225 bushels per acre, well, I got 175 bushel grain sorghum. Nobody's talking profits. Nobody's talking inputs versus outputs, and there's a way, way bigger opportunity for more profitability, which means you're gonna get a lot more off the same acres if you just pay attention to this stuff.
Absolutely. Yeah, there's no question about that. So, usually, we have these seminars and these conversations in January and February when people have the time to sit down and have longer conversations, and we have more time throughout the day. Today, that is not the case. We're supposed to be done here at 2 o'clock this afternoon. We've got about an hour to lunchtime and about an hour afterwards. There's lots of things to talk about. Because of that, we have often the feedback that we get at conferences, seminars. One of the things that we have really taken pride in as a company is providing a lot of information, explaining the why. Why does this work? How does it work? How can you make it work on our farm? We give the growers that we work with and the people who come to our seminars enough information that they don't need us to figure it out. They can go onto their farms and do it themselves. They don't need to use our products. They don't need us to figure it out. They can take our information and do it by themselves. However, the feedback that we have gotten quite consistently is that people are frustrated that we don't talk enough about the products and actually how do you do it. What's step 1, step 2, step 3? What are the problems that we see and what do you actually do about it? So as a result of that feedback, today we're going to split this conversation into 2 different pieces. One is for the next hour or so until lunchtime, I want to talk about the why. What is happening? Why do we have problems with spider mites and sugarcane aphid and all the various insect pests that you listed off? Why are they present in the first place? And what can you do about it? I want to talk about that piece until between now and lunch. And then immediately after lunch, David and I will both be talking about, okay, what do you do about it? And because of the limited time, I do not want to sound crude or rude when I say this, and I don't intend it in that way at all, but I'm going to be very candid. I'm not going to pull any punches. I'm going to say exactly I've been here in Kansas now several times. I'm going to say exactly from my perception what I'm seeing is the problem, why we're having the problems that you're having from the management practices that you're using, and what we can do to fix them. It's going to be straight talk because we only have time for straight talk. There was something else I wanted to mention as well, and now it's escaping me for the moment. Okay, so we're going to jump right into this. Let's talk about why we have insects showing up, why we have diseases showing up, what they are dependent on, and what we can do about them. So, actually, I'm going to skip through some of these. This is some of the background of where we came from. A lot of our knowledge originally came from the fruit and vegetable production world. And I think this is worthwhile mentioning. You may think that, well, fruits and vegetables are very different from growing corn. And I'm not sure this conversation is really worth listening to. But the reality is, when you have a strawberry crop in California that's worth $40,000 an acre, you had better not screw it up. You had better not screw it up. So our history really is in working with very high risk, high value crops where any mistake that you make can end up in a lawsuit really easily. So we've We've learned in how to deal with these very intense crops, very intense management, and we've learned a lot about plant physiology that applies very well to corn and soybeans that we'll be talking about in a little bit. This is table grape production in California. This is a table grape cluster that will probably end up weighing about 8 to 10 pounds when it's fully mature. This is what the entire field looks like. So, starting point. We'll begin with the concept that healthy plants can be completely resistant to diseases and insects. The idea within agriculture is that insects and diseases show up at random. They attack fields at random. They're here in this one field or in that field. And it just happens based on wind conditions or climatic conditions and so forth. And that certainly is a contributing factor, but it is not the only contributing factor. In fact, it may not be even the biggest contributing factor. So I want to talk about, and so diseases and insects do not occur at random. There's actually a tremendous amount of research about plant immune systems. I'm not going to go into this. Just to give you a couple of examples, here are 2 books that talk about plant immune systems. Here are 2 more. Here are 2 more. And here's another one that talks about mineral nutrition and plant disease. My point is that there are hundreds of articles, no, thousands of articles, dozens of books that have been written about plant immune systems. There's several journals as well. And for the most part, that information is not talked about in agricultural circles because there are no economic incentives for pesticide companies to get this information out there. All right, so I want to talk about what the differences are between healthy plants and unhealthy plants. We understand that every living organism has different nutritional requirements. So our nutritional requirements that we require for our own body and the food sources that we require, specifically I should say food sources, that we require for our own body are quite different from those of, let's say, a cow. And we are capable of digesting things that a cow is not capable of digesting, and vice versa. A cow can digest things that we can't digest. Why? Because the enzyme systems in our gut are completely different. So with a cow, for example, a cow can digest grasses and forages because she has cellulase enzymes in her rumen in the digestive system, so she can break down cellulose. We, on the other hand, have the enzymes and the acids that are needed to break down very long, very complex proteins found in muscle meat. So we can digest meat. A cow can't do that. That same concept, same idea holds true irregardless of what organism you're talking about, including insects. This is very important because every insect, the insect pests that you listed off this morning, all have specific nutritional requirements in 2 groups. First is proteins. They have very specific protein and amino acid requirements. And secondly, they have very specific carbohydrate requirements, very specific types of sugars. So it is possible to change the plant's amino acid profile and to change a plant's carbohydrate profile so that they are no longer a food source for the insect. So when we talk about plant immune systems, there are 2 different types of immunity, or 2 different ways of thinking about it. One is passive immunity, and the second is active immunity. So with passive immunity, this is what I'm talking about when I talk about passive immunity. We're simply removing the food source. You put grass on the kitchen table for lunch, and that grass is passively immune to being consumed because nobody wants to consume it. You've removed the food source. Active immunity is a little bit different. Active immunity is when plants are so healthy and so vigorous that they're actually producing these immune compounds that have the capacity to kill bacteria, to kill fungi, and to kill insects. So those are the differences between active and passive. For the moment, we're going to talk about passive immunity. So, when a plant is photosynthesizing, everything starts with photosynthesis. So, photosynthesis is the foundation. The plant is absorbing water from the soil, it's absorbing carbon dioxide from the air, and it's combining those into a simple sugar called glucose. So glucose is C6H12O6. Forget the chemistry formula. Think of glucose as being a short chain that has 24 links. It's 24 links long. Okay? Now, that glucose then gets snipped apart, cut apart, rearranged, rebonded, stuck back together again to form much longer, more complex chains. So sometimes when glucose is aggregated, when you have an aggregation of different glucose together, you end up with starch. Perhaps it's restructured in different ways. You can end up with, you have these different types of sugars. You have the monosaccharides, which are simple sugars, short chain sugars. You have polysaccharides. Then you have compounds such as lignin and cellulose and hemicellulose and pectins. These are all structural carbohydrates that build part of the plant frame. They all start with this simple building block, this Lego brick that has 24 links. That's it. It's that simple. That's the carbohydrate side. On the protein side, you again start with this short chain that has 24 links, and it's now reorganized, and nitrogen gets added to it. The combination of sugars plus nitrogen is now called an amino acid. So there are 23 common amino acids that are found in plants. There's several hundred others as well, but 23 main ones. And those amino acids are now hooked together in pairs of 2 or 3. And now they're called peptides. You may have heard of a dipeptide or a tripeptide. That's simply 2 amino acids or 3 amino acids bonded together. And then those peptides are now bonded together to form much longer chains that are now called complete proteins. I know I'm boring all of you with this, but this is really important. This is a very important piece. Imagine that happening inside a plant. Constantly, all the time. This is the way sugars get built. This is the way amino acids get built. This is the way peptides get built. But now, imagine also, you have this raw chain. And now, when we talk about amino acids being bonded together, one amino acid to another amino acid, inside the plant needs a catalyst to make that reaction happening. There is a welding crew inside the plant that is cutting this chain apart into various links and reassembling it and putting it back together again in various configurations. And this welding crew are enzymes. Enzymes are crystalline proteins. They're shaped like a crystal. Enzymes are fascinating in that when I talk about a welding crew, they are very much like a welding crew in that the way an enzyme works by this crystal function is by collecting and absorbing photonic energy and releasing it in a beam, almost like a miniature laser beam as a blast. That's how it puts these bonds together and also takes these bonds apart. But you look at this enzyme, this crystal is dormant. There's nothing happening. These enzymes are completely 100% dependent on what is called an enzyme cofactor. So you bring in an enzyme cofactor, zinc, manganese, copper, boron, and that manganese cofactor, the enzyme cofactor are all these metal ions. Without the metal, the enzyme doesn't work. It's dead. So what happens, let's talk about enzymes a little bit more. Enzymes are like an end wrench in that each end wrench fits only one size nut or bolt properly. And each enzyme can only produce one specific reaction. It can only tie one specific amino acid to another specific amino acid. So as a result of that, because there are dozens of amino acids, dozens of carbohydrates, thousands of possible combinations, plants have over 10,000 different enzymes that have been identified so far. And every single one of these enzymes needs an enzyme cofactor. So what this means is if the enzyme cofactor is missing, let's say a plant is missing manganese or zinc or one of these metals, that means that all of those enzymes that are dependent on that cofactor don't work. The machinery doesn't work. So it's like that chain manufacturing machine that we saw, where one of the arms is out of alignment and every link gets misshaped. The entire machinery breaks down without the enzyme cofactors. Okay? So, why does this even matter? Why is this even worth talking about? Why is it worth me spending the last 10 minutes talking about this? Because the digestive process in the digestive system of an insect or a cow or our own digestive system is exactly the same as this process of building compounds inside plants, except in reverse. Now, instead of having enzymes to build all these bonds and to put all these chains together, we now have enzymes that are designed to break apart the bonds. They take apart the various peptides, they take apart the amino acids, and they break it down to a point where it is soluble enough that it can cross the gut lining and be used as an energy source by the cow or the person or the aphid. The key is that the enzyme system of an aphid is radically different from the enzyme system of a cow or of a human. And what this means we refer to some groups of insects as insects that have simple digestive systems. What it means very simply is that you have this progression. You start with glucose, you add nitrogen, you now have an amino acid, you bond 2 or 3 amino acids together, now you have a peptide, and then you bond the peptides together to form complete proteins. So these complete proteins might be chains that have as many as 200 to 300,000 links. Well, guess what? Sugarcane aphids and all larval insects such as corn earworm and cabbage looper and tomato hornworm and alfalfa weevil and so forth do not have the digestive enzymes that are needed to break the peptide-to-peptide bond that is used to make a complete protein. So if you have a plant that has a completely functioning enzyme system and it is building complete proteins and complete carbohydrates, then you have removed the food source. You've simply taken away the food source that the aphids and the other insects and spider mites are dependent upon. They can't feed on that plant anymore, literally the exact same way that you could not consume grass, because they can't digest it, they can't break it down. Enzymes are like end wrenches in another context as well, that they never get used up. An end wrench can tighten 100,000 nuts and bolts. An enzyme can do the same thing. It can produce that same type of reaction over and over and over again without being consumed. That's why you only need very small concentrations. These enzyme cofactors are all either metals, like copper, cobalt, iron, manganese, magnesium, etc., or they are B vitamins, which in turn are dependent on metals. So B vitamins like vitamin B12, cyanocobalamin, is dependent on cobalt, etc. So I feel almost as though I'm doing you a bit of an injustice because I'm condensing a lot of this down very simply, but I want to make sure you got the piece that I just have been talking about. Is it all clear? Clear as mud? Okay.
It's the whole key to the whole thing that goes on in plants.
I've just condensed an entire plant physiology semester at a university down into 10 minutes. It's basically what it amounts to. This is the only thing that really matters. Yes?
John, tell this crowd about those mentors that you got together and their previous experience with finding a cure?
Yeah, I'm not even sure. That's not appropriate for all audiences. Well, I was very fortunate. I developed the first year I had 7 mentors, and the next year 10. And there's been many mentors over the years. I still have a group of mentors that I work with today. But in the first group that I work with, when I started asking questions about plant immune systems and resistance to diseases in insects, I quickly discovered that there were not very many people who were able to answer the questions that I was asking. But there was one group in particular, 3 friends who'd known each other and worked together at one point, who were able to answer all my questions almost right off the top of their head. These were Don Huber and Michael McNeil and Bob Kramer, who were 3 out of the original 7. And the reason they knew so in depth about how to manage diseases and insects using nutrition was because of their military experience in the 70s. Don Huber has now retired from the Army, but is still a consultant for them. Don Huber was the colonel who was in charge of biological warfare research for agricultural crops at Fort Detrick, Maryland during the Cold War with Russia. And Bob Kramer and Michael McNeil worked underneath of him, and the task that they were given was to identify all of the potential biological warfare agents that Russia was working with that could possibly be deployed on food crops, and to develop a solution for them. So if there was an epidemic of disease, they needed to know how to stop that disease instantly and prevent it from costing the United States its food supply. And the solutions that they developed to all of these diseases were nutritional solutions. So they could identify if we had problems with, it's funny because they were working with soybean rust in the laboratory in the 70s. And when soybean rust first came out in the Midwest, had conversations with them, and they said, yeah, we know what this is. We know all about it. We know exactly how to deal with it nutritionally, too. This is not new information. It's been out there for a long time. So I don't know if that was what you were asking for or not, but...
It's just, it's kind of a shift in thinking. We think that we've got to go out and buy a commercial produced product or a synthetic to alter or to get us results when it's the protein. It's actually a natural.
Exactly. Every one of these organisms, even all these disease organisms, the pathogens, right now, we have major problems with HLB and citrus greening. Supposed to be this huge, insurmountable problem. Well, as a company, we have worked with one citrus grower in particular where we completely reversed citrus greening in 18 months. Reversed it. It's gone. But do you think we could get anybody in the citrus industry to listen to that? They're not interested. It's not a GMO plant, and they want a GMO plant. Anyway, no point in having that conversation. So, this next piece that I'd like to talk about, as we have worked with growers, hundreds of growers, thousands of growers, many different types of plants, many different types of environments, we have observed a consistent shift, an evolution of plant health in all these different crops that is consistent irregardless of the crop, where they become resistant to different types of diseases, different types of insects, based on what is happening inside that plant physiologically. So we developed this diagram that we call the plant health pyramid to describe what we saw happening inside plants. There is a lot of information in this plant health pyramid. I'm going to review it in about 10 minutes or less. And if you want to learn more, you can also, I think we have a YouTube clip on YouTube that you can look at and review and get more information from it as well. But this is what we see happening. And there might actually be a handout in your folders that has the plant health pyramid on it. If not, there's a number of articles and YouTube clips online on our website that you can access as well with more information on it. So the first piece that we see happening is when we have plants that are photosynthesizing well and they're producing complete carbohydrates. The moment the plant begins producing complete carbohydrates, what this means is that every 24 hours, in every 24-hour photoperiod, at the end of that 24 hours, 100% of the sugars produced in that photoperiod have been converted to complete carbohydrates. In other words, they're pectins, lignans, cellulose, hemicellulose. You do not have any simple sugars, such as glucose, left over in the plant sap. It's all been converted. When it has all been converted, you've now removed the food source and removed the soluble sugars that are dependent on, required by the soil-borne fungal pathogens. So these soil-borne pathogens are Verticillium, Phytophthora, Pythium, Fusarium. All of these soil-borne fungi are dependent on plants that have high levels of soluble sugars and soluble carbohydrates. And again, I could talk about that for 30 minutes, but we're going to keep moving. The second level is when plants begin forming complete proteins. I described this process for you. The moment these plants begin forming complete proteins, which means they have no nitrate in plant sap, they have no ammonium in the plant sap, and they have no soluble amino acids in the plant sap. The day that happens, you've removed the food source for all of these insects that have simple digestive systems. So the simple digestive systems are insects such as aphids, corn, all the larval insects belong in this group. Anything that is a larvae has a simple digestive system. And all the sucking and chewing insects, spider mites are technically not an insect, but they belong in this group. Aphids are in this group, leafhoppers are in this group. And I was looking at the list that you guys were discussing this morning. Spider mites, rootworm caterpillar, alfalfa caterpillar, beet armyworms. Beet armyworms are a bit of a question, but they are in the caterpillar family, or in the larvae family. Sugarcane aphids, corn earworms, all belong in this second group. They're all here in the second group. And I'm really excited about that. Why? Because these first two levels, the first two levels of the plant health pyramid, we have been extremely successful at producing plants with these first two levels in a very straightforward fashion. These first two levels are purely a result of balancing the chemistry and balancing the nutrition inside a plant. You can do this in a hydroponic system. It does not take soil. It doesn't take biology. It's very straightforward. Then, you get to level 3. Level 3 is a bit different. Level 3, the plant begins, it has a surplus of energy. It's photosynthesizing so well, it's absorbing nutrients so well that it has more energy than it needs for its own use. So it begins storing the surplus in the form of fats and oils, lipids. Exact same thing that happens with an animal. You give it more feed and more energy than it requires, it stores the surplus as fat. Plants do exactly the same thing. When you see this, when plants begin producing these higher levels of lipids, you see this glossy, waxy sheen on the leaf surface. And with that glossy, waxy sheen, these plants now become resistant to all of the airborne pathogens, bacteria, fungi, downy mildew, powdery mildew, scab, speck, spot, etc. The list goes on and on. Anything that lands on the leaf surface, how does this work? Just a simple explanation. Again, it's all about enzymes. When a bacteria or a fungi lands on the leaf surface, most of them, I think actually practically all of them, release an enzyme that is called a pectolytic enzyme, meaning it is designed to digest and break down pectins, specifically the pectins that are found in the cell membrane, so that it can go through the cell membrane into the cell and use the nutrients contained within that cell as an energy source. And the result is an infection. Well, if you have a plant that has high levels of lipids and you have this waxy layer on the leaf surface, you have a shield. The fungi or the bacteria lands, it releases a pectolytic enzyme, but in order for that, remember, the enzyme can only do one thing, that's digest pectin. If you have wax there, it can't do anything. It's shut off before it ever starts. So the result is you never get an infection. Level 4 is when plants begin producing high concentrations of these compounds called plant secondary metabolites. In plain English, we call them essential oils. These compounds are compounds such as anthocyanins, resveratrol found in red wine, lycopene found in tomatoes, phytoalexins, terpenoids, sesquiterpenes, bioflavonoids. These are all compounds that plants produce as plant protectants to protect themselves from ultraviolet radiation, from disease attack, from insect attack. These compounds at the top of the pyramid have the capacity to kill on contact. Bacteria, that many of them have very intense, very potent bactericidal and fungicidal properties. And what we see is that plants, this is where we're talking about active immunity, where plants are actively going after diseases and insects. And at this stage, these plants also become resistant to all of the beetle family. Japanese beetle, corn rootworm beetle, marmorated stink bug, Colorado potato beetle, etc. Now, level 1 and level 2, in our experience, are very straightforward. Level 3 and level 4, in order for you to get to level 3, you must have good soil biology. Not maybe, not perhaps, not if. You must have good soil biology. You cannot achieve that in a hydroponic situation. Because, well, again, lots of science behind this, but very simply, when you have really aggressive soil biology, nutrient absorption from the soil becomes much more efficient, and plants now have a surplus of energy that they can convert into lipids and store as fats. All right, I have to keep moving here.
I have one question.
Yep.
If and I'm not an expert, but like say a rootworm beetle is eating silk, like if everything is in place, will it not clip those silk?
First of all, it won't be attractive to them. Secondly, if you have a plant, and we've actually observed this, if you have a plant that is, let's say, the nutrition is for the most part balanced, but it is deficient in magnesium and manganese. I'm making up a hypothetical scenario. And as a result of those two deficiencies, the plant is not doing well, and you have corn rootworm beetles present, and they're actively feeding on the plant. And you put on a foliar spray that precisely addresses what that plant needs. While the cucumber beetles are present, that plant's chemistry changes, the protein profile changes, and it will actually kill the insects that are already on the plant. We've seen this with Colorado potato beetle, we've seen it with corn rootworm beetle, we've seen it with Japanese beetle, we've seen it with corn earworm. It's a ton of fun.
And the way you get to, like, how do you know, is that with tissue samples? To
Yes.
find out what?
Yeah, you have to, we use sap analysis, I'll be talking about that in a little bit, but guessing doesn't work. You have to know exactly what's going on in order for you to get those types of results. Yeah.
Was that within 24 hours? Or?
It varies depending on other stuff that's going on, the stage of the plant, the climate, and so forth, but I'd say usually it's within 24 to 72 hours. That's what Brad saw with the spider mites. That was 48 hours, they were gone. So it happens pretty quickly. It certainly happens quickly enough to be an effective consideration for replacement for insecticides, that's for sure. So, do insects and diseases occur at random? Or are insects attracted to plants at random? According to the research work of Dr. Philip Callahan, the answer is no. Philip Callahan was an entomology researcher at the University of Florida, Gainesville. His research work was actually financed by the U.S. military. This is again during the 70s, 80s, 90s. And he published over 400 papers that were classified for a long period because his research work was actually the basis of the military developing anti-radar cloaking devices for military aircraft. And that technology has now been exceeded, so all these papers have been declassified. He also published a number of books for public consumption. But what he described in his research, again, this is simplifying and gelling things down very simply. He said that, this is a quote from William Albrecht, "Insects are nature's garbage collectors and diseases are her cleanup crew. They're here to take the unhealthy plants out of the system." Philip Callahan demonstrated this and proved this with his research. Several of the books that he wrote, if you want to learn more, you can read this one, Tuning into Nature, is really good. This is actually the bottom side of a tomato leaf, 4,000 times magnification. All of these are micro antenna vibrating at 26,000 megahertz. This is an antenna that we actually call an antenna. The only difference between this antenna and this antenna is the optimal frequencies that it picks up. Fundamental. It's the only fundamental difference, the different wavelengths that they absorb. So this is that moth antenna, also underneath a microscope. And now, when you take one of those smallest hairs and you put that underneath a microscope, this is what that looks like. It's like fractal geometry. You have antenna upon antenna upon antenna. And all these antennae are communicating specifically in the infrared spectrum. They pick up wavelengths from throughout the electromagnetic spectrum, but they are primarily in the infrared spectrum. They're communicating with their environment and what is happening around them. So based on this research that Philip Callahan did, what he described is that when we see healthy plants out in the field that are dark, vigorous, growing well, this is what we see. When we have unhealthy plants that are not doing well, have insects present, this is what we see, and this is what insects see. In Dr. Philip Callahan's own words, and this is a direct quote, he said that unhealthy plants which have a high ammonium content stand out in the infrared spectrum like a neon light against a dark background. They stand out that strongly. And specifically, he mentioned ammonium. Why is ammonium a problem? Because ammonium The ammonium compound is what is called an infrared signal pump. It's an amplifier. Whenever you have ammonium present, it will produce a tremendous flash and a signal in the infrared spectrum. So this is why when you go out and spray an insecticide and you spray a plant and you eliminate all the insects, you haven't fixed the problem because the sign is still there. You're just going to be inviting, you still have the welcome sign for the next wave of insects that's going to come along. If you want to remove that signal, if you want to fix the problem, you have to fix it at its source and remove the signal in the first place, and then the insects are not going to show up. How do we actually make this work, and how do we make it work in the field? So I've given you a very quick introduction and background to kind of our thinking and how we approach these problems, what the underlying causes are, and now it's time to start talking about, okay, what are the nutrient interactions and what is it that you need to manage in the field? So this is a chart that describes all the various nutrient mineral interactions. How many of you have seen this chart before? How many of you have memorized it? Oh, come on. That's exactly the point. We haven't memorized it. We don't remember and retain what is in this chart because it's too complicated. There's too much information and it's not obvious, it's not clear. So actually, let me back up just a step, give you a little bit of history and context for this. I had read tens of thousands of white papers and books and everything else about plant immunity and plant disease and correlation of disease with specific nutritional profiles. And it was intensely frustrating as a consultant that I could not see in the field what all the research indicated should be true. For example, when we talk about powdery mildew, there are at least 40 published peer-reviewed white papers that describe a clear correlation between powdery mildew presence and manganese levels. It's there. It's well recognized. But when we were doing tissue analysis and pulling leaf tissue, sending them to laboratory, having them analyzed, there was no correlation between the manganese content in the tissue analysis and the powdery mildew content in the field. It was intensely frustrating. The research said it should be there. The practical application said it wasn't there. So in 2010, December 2010, I was at a national conference and was speaking with several of my mentors who were also present, and I was expressing my frustration with our inability to clearly see what was happening and what was going on. And one of them suggested that I reach out to a laboratory in the Netherlands that he'd become familiar with, who had developed a process for measuring the nutrient content of plant sap. They were calling it simply plant sap analysis. We started using plant sap analysis in 2011. We used it on an experimental basis for 3 years, 2011, 12, and 13. 2014, we started using it very intensely. Today, we run tens of thousands of samples a year of plant sap analysis. Think of it this way. Plant sap analysis is radically different from tissue analysis. It's not even in the same league. It's not even in the same ballpark. I absolutely love it. I could talk about sap analysis for a long time as well. But the fundamental difference between sap analysis and tissue analysis is this. Tissue analysis, you collect a leaf, you send it to the laboratory, they ash it. They dehydrate it down to an ash. They measure the mineral content of the ash, and they report it on a dry matter basis. Sap analysis, you collect fresh leaves, you package them in a Ziploc bag to keep them fresh, you overnight them to the laboratory, they extract the sap out of the leaf itself, they don't dry it down, and they measure the nutrient content of the sap itself. So that is the equivalent. This is a bit of a crude analogy, but let's say I want to know whether I have enough calcium. So I can take a blood analysis to see whether I have enough calcium, or I can cut my hand off and measure my hand to see if I have enough calcium. Of course, when I measure the calcium contained in my hand, it's going to come back extremely high because there's a lot of calcium present in the bones. But that means absolutely nothing about the amount of calcium that I actually have available. The same holds true in plants as well. There are a lot of minerals that are locked up inside cell membranes and cell matrices that are not necessarily available to plants. So, long story short, sap analysis is so powerful that we have been able, with crops that we are familiar with and have extensive experience with, we can actually predict disease or insect susceptibility based on a plant's nutritional profile. We have never been able to do that before in agriculture, ever. Think about it. When you go to a doctor The doctor has a difficult time making a diagnosis, doesn't understand what's going on. What's the first thing that they do? They pull a blood sample. They send the blood sample to the laboratory. In the laboratory, they do a nutritional profile of the various amino acids and enzymes and nutrients that are contained in that blood. And from that nutritional profile, they use that to make a diagnosis about how well various organs in your body are functioning. We have all of the science, all the background science, to do the exact same thing for plants, but we never had the laboratory analysis that was accurate enough to allow us to do that. Today we have that. This is a story that I believe is very important. The first time, we were still learning plant sap analysis, gaining familiarity with it, becoming comfortable with it. And I still remember the first time that I felt extremely excited about sap analysis. This was in midsummer, late summer 2013. One of our consultants, Gary Redding, was working with a hops grower in Washington. Yakima, Washington, 1,100 acres of hops. At that time, one of the largest hops ranches in the country. Actually, I think maybe still the largest. They had been pulling sap analysis samples on all their various blocks every 2 weeks throughout the growing season up until harvest. So this was now post-harvest. They had harvested earlier in the year, and they wanted to begin thinking about and preparing for next year. So they asked for a conference call. They put all their samples together into a spreadsheet, sent me the spreadsheet, and we jumped onto a conference call. There were 5 of us. On our end was Gary Redding and myself on AEA, and on their end was Mike and Sam Turner, the farm owner, and his son, and their local agronomist. At the beginning of the call, I told them, I said, look guys, I don't know anything about hops. I have never worked with hops before. I have no idea what their nutritional requirements are. I have no idea what diseases and insects they're susceptible to. I said, to the best of my knowledge, I've never even seen a live hops plant in my life. The ranch owner responded and said, well, between the 3 of us on our end, we have a combined 81 years of experience growing hops. And we think that with our experience growing hops and your understanding of plant physiology, we should be able to figure it out. So I started looking at all the data and the spreadsheet that they'd sent over, started asking questions about their nutrient applications in the irrigation system and with foliar sprays to try to understand some of the fluctuations that I was seeing. And then about 10 minutes into the call, I said, okay. Again, with the disclaimer that I really don't know what I'm talking about. Based on experiences with other crops and based on seeing these nutrient interactions and how the nutrients are moving around, I suspect that this crop is very susceptible to either downy or powdery mildew, I'm not sure which one, but one of those 2, and spider mites and whiteflies. And there was dead silence on the phone for about 10 seconds. And then Mike says, well, maybe you know more about growing hops than we do. He said, our top 3 pests are powdery mildew and spider mites and whiteflies. That was, yes, that was a big moment for me, because for the first time, we had a lab report that was so accurate that we could actually predict disease and insect susceptibility based on the plant's nutritional profile. This is powerful because now it means not only can we predict it, it means we also have the information and know what to do about it. So we now know what to do to manage it. So, from our work with sap analysis, and by the way, I'm not going to expand more on sap analysis later. Again, you can go to our website, you can go to the Crop Health Labs website, you can get all kinds of instruction manuals on how samples are to be collected, etc. But I will make this very clear, very simply. On any we do not pretend that we know all the answers, that we have it all figured out, because we don't. There are a lot of things that we don't know. There are lots of insects that we don't have prior experience with. There's weeds we don't have prior experience with. There's a lot of things that we don't know. But I think what we feel that we do know and what we do have is we have the tools and the mental framework and mindset to figure it out. As a result of that, any farm that we work with in Kansas, we want to work with you guys to help you with some of the problems that you're experiencing. We will only do that if you're committed to taking plant sap analysis so that we can see what's going on. Every recommendation that we make, everything that we do is based on data. We don't guess. We don't have the luxury of guessing. We are passionate about figuring it out and doing it properly. We're not going to guess. All right, let's go back to talking about nutrient interactions. Based on all of our experience with sap analysis, the team in the Netherlands who developed this technology developed their own nutrient interactions chart, and then we took that and modified it a little bit. And this is the new nutrient interactions chart that we have put together. It's a lot simpler, it's a lot easier to understand, and there are a few lessons that it drives home that are very, very important. So the idea is, the upper half of the chart we have cations, macronutrients. Lower half we have micronutrients. Left side we have the positively charged cations. Right side we have the negatively charged anions. So we have 4 different quarters. And for all the major elements at the top of the chart, all of these elements, all of these macronutrient cations antagonize each other inside the plant. So think of it, when we talk about soils and mineral holding capacity in soils, we have this concept of CEC, cation exchange capacity, and we understand that a soil has a finite mineral holding capacity. It can only hold so much. And we haven't used that same type of thinking about plants and plant cells, when in reality it's also true. Each cell can only hold so many minerals. So all of these elements will add up to 100% inside a plant. And if you have an excess of one, it will create a deficiency of something else. It will prevent the plant from absorbing something else. And this holds true of all the cations. It also holds true of all of the anions. I'm not sure if you realize the gravity of what I just said. In agriculture, we have approached the plant nutrition challenges with the paradigm and the perception that we constantly need to add more. We don't have enough zinc, we need to add more. We don't have enough manganese, we need to add more. We don't have enough potash, phosphorus, nitrogen, we need to add more. When we started using sap analysis and we started understanding these nutrient interactions, it became really, really obvious, like 2x4 in the face obvious, that most of the problems that growers are experiencing are not a result of deficiencies. They are a result of the excesses of the product the farmer is applying that are creating the deficiencies. That is the problem, 90% of the time. If you look at this, if you have problems with potassium and calcium absorption, it could very easily be because you have excessive ammonia in the system. On the other side of the chart, if you have problems with phosphorus absorption, it could be because you have too much nitrate in the system. Anything that is excessive will create deficiencies of some or all of the other nutrients on that side of the chart. And we'll talk more about this in a little bit. All right, this is a concept that we developed a couple of years ago called critical points of influence. And it is the idea that there are critical windows within a plant's growth cycle and reproductive cycle at which any level of stress or any nutrient application is going to have a completely disproportionate impact on overall yield and overall plant performance. So these critical points of influence are fundamentally tied to the plant's reproductive cycle. So the question that we need to think about is, where are the moments where reproduction is being affected? And there's really fun conversations about hormones, hormone shifts, hormone cycling, nutrient interactions, and so forth. But we're going to keep it very elementary for the moment. If we look at corn, this is research that was done at the University of Iowa in the early 90s. They said that 9 to 12 days after a corn seed germinates, it is determining the number of ears that it could potentially have. Not that it will have, but that it could potentially have. Embryo initiation is already happening at that stage. That's a 3-day window. Then, 14 to 21 days, the plant is determining the number of rows that it could potentially have. And 42 to 49 days after germination is determining the number of kernels per row. So now, when you think about that, and you look at that in aggregate, there's a couple of really interesting points that are revealed here. First of all, the greatest influencing factor on yield is determined earliest in the plant's life. If you can influence the number of ears, you're going to have a much bigger impact on yield than the number of rows or kernels. Secondly, look at the narrowness of the windows. That first window is 3 days. So the way to think about this is, the question is about stress. Any level of stress that happens to that plant in that 3-day window is going to reduce the number of ear embryos that that plant is going to set. So if that 3-day window happens to occur when you have some cold, wet, stormy weather, or some hot, dry, windy weather, whatever the case might be, that's going to have a substantial impact on that plant. Versus if it happened 2 days earlier, it would have a lot less of an impact on the overall yield potential. So if you look at this, the way to think about this is when we talk about genetic potential, you talk with any of the corn breeders, plant geneticists today, they will tell you that 100% of all the corn genetics available in the marketplace today have the inherent genetic capacity to produce a minimum of 1,100 bushels per acre of corn. That's standard industry knowledge. But we're harvesting 150, 180, 200, 250, whatever the number might be, depending on our production system. So what happens is the day we plant that seed has the potential for 1,100. Perhaps it wasn't planted properly, wasn't covered properly, doesn't have good moisture contact, and now you've reduced it from 1,100 down to 1,000. Perhaps fertilizer wasn't placed properly, doesn't have good nutrient access, and now you've reduced it from 1,000 down to 950. Perhaps in the 9 to 12 day window, it's exposed to a severe storm, you've reduced it from 950 down to 800. Whatever it is, I'm just making up a hypothetical situation. The point being that throughout the entire growing season, every time that plant encounters stress, it reduces the plant's yield potential. At the point where you're finally harvesting the crop, you're harvesting only a very small fraction of what you originally started out with. Why does this matter? It matters because what this means, every time you do something that makes a yield difference, whether it's applying a fungicide or an insecticide or a fertilizer or irrigation, doesn't matter what it is, every time you do something that makes a yield improvement, you have not increased yields. You have simply kept those yields from being lost. Doesn't seem like a major shift, but it's a very important, very fundamental mind shift. So the question becomes now, okay, if we want to produce higher yields and higher quality, higher test weight, whatever the context of the conversation, the key is that if we want to reduce yield loss, we simply reduce stress at these critical points of influence, or we make the plants a lot more resilient to stress. And this is something, again, that can be managed with nutrition. You can't remove the hailstorm, and there's obviously some stresses that you can't protect against, but you can still give a plant a lot more resilience to climactic stress, whether that's hot, cold, wind, dry, whatever the case might be. So this is a diagram that we put together to describe critical points of influence. There's too much for me to go into here. Yeah, sorry, we don't have the luxury of time. How many cycles do you think a corn plant has when it switches? So these reproductive cycles, we're talking about a plant that is, first it's growing vegetatively, and then it switches, there's a hormone shift. It shifts to reproduction, then it switches back to vegetative growth, and then it switches back to reproduction. With cherry tree, for example, we start in the spring with blossoming. There's a very strong reproductive shift. And then it switches to vegetation. In vegetation, we get early on, we get leafing out and very rapid shoot growth. And then it switches back again to reproduction, where we get very strong fruit fill. Then it switches back again to vegetation, and we get more shoot growth. Then it switches back to reproduction, and we get bud initiation for next year's crop. So there's this constant cycle happening where the plants switch back and forth. How many cycles do you think a corn plant has? Any guesses?
200 to 300.
200 to 300? Not quite that many. That would be more than one per day. 13. 13 different periods where it switches from vegetative to reproductive. So you look at this and you might ask the question, well, why is this even worth talking about? Why did we just spend 10 minutes talking about this? Because obviously it's very important from a yield perspective. It's also very important from a disease and insect resistance perspective, because when plants switch from vegetation to reproduction, there's a tremendous hormonal shift that happens. If we go back, I'll give you an extreme example. Well, corn also is appropriate, but one of the more extreme hormonal shifts in a corn plant is at pollination. It's the equivalent of a pregnancy. It's basically what's happening. All these seeds have become fertilized, and now they're viable embryos, and now they're starting to grow. So you have this tremendous hormonal shift that happens. And as that hormonal shift, if it is not supported with the right nutrition, that plant automatically switches. The scientific terminology for this is protein synthesis versus proteolysis. When I was talking about protein synthesis earlier, that plant will, if that is not supported with the right nutrition, it will automatically switch from disease resistant to disease susceptible, just like that. So those windows are really important to support properly with the right nutrition. The entire point of me going through this explanation is that when we as a consulting group at AEA say that you need to apply XYZ products in this time window, we do not mean 2 weeks earlier or 2 weeks later. It needs to be applied in this time window. Now, corn and many grain crops, we have the luxury that we have some fluidity with many of these time cycles, particularly later on in the plant's development, where we might have a week or 10 days time window with which to put on a product application. On a cherry crop or an apple crop, you might have 3 days is your golden window of opportunity. So obviously, there are management considerations here. It's not possible to apply a product on a large number of farms within a very condensed time windows, sometimes from a logistics perspective, but the reality is that timing is absolutely critical. If you miss your golden window, you can have, well, I can think of any number of examples, but I'll just use one that comes to mind right now as a corn grower in the Pacific Northwest who missed a foliar application that we wanted to happen right at ear silking and pollination. And he put on the foliar application on 2 sections, and he got a 30 bushel per acre yield response. And the remaining 5 sections did not get the application until 5 days later. He got a 7 bushel yield response. Purely based on timing. Exact same product, same application, different time, completely different result. Perhaps to kick off this afternoon, I first want to begin with an example of a farm that we worked on. I believe this is 2012 growing season, if I'm not mistaken. This is a farm in central Indiana, just north of Indianapolis a little bit. 2012, they had an extremely dry growing season. 0.6 of an inch of rain from the beginning of May until the end of July or something like that. I used to have all the numbers and dates right off the top of my head. This is an organic farm. They've been organic for 30 plus years, and they were growing blue food-grade corn. This blue food-grade corn, organically certified corn in the Midwest, there's not any extremely productive varieties. With this variety that they were growing on this farm, they were typically, Midwest yield averages were about 90 to 95 bushels an acre. This farm has been growing blue corn for the 4 years prior, with a little bit better average than that. They were consistently doing around 100, 105. The best that they had ever done was 110 bushels per acre. So in 2012, we started working with them that spring. We had not done anything in the fall prior. We started working with them in the spring, and we did an in-furrow application of nutritional solution, and we had intended to do 2 foliar applications of nutrients. We ended up doing 3 because they had an extended, really hot, dry period. The plants were really stressed, and we wanted to put on a 3rd foliar just to help the plants through that period. So we ended up doing 3 foliar applications. So they got into the field at harvest time. I'm not even sure if I have all the data on these slides. This is a photo that was taken on the end of July, in the middle of a 10-day stretch of 100+ degree temps and high winds. At harvest time, when they took the combine into the field, they had 170 bushels per acre, over a prior 4-year average on this farm for this variety of 105. That was really interesting. But the other interesting part was
This was one of those operations where we saw a substantial increase in soil organic matter. We saw a jump in soil organic matter while we were growing this crop before and after. And so we started asking the questions, how is this possible? How do we get these types of results? And how do we replicate these types of results consistently across other crops? So in addition, there were substantial color differences. The blue corn was colored a lot darker, a lot better. And the test weight increased from a prior 4-year average of 56 up to 59.1 pounds per bushel. So a substantial increase in test weight as well. So not only was there an increase in bushel volume, but an increase in test weight as well. Now this was in a year, I don't think I adequately described this, in 2012 throughout this region of the Midwest. In this local region, the local county where this farm was, 70% of the corn acres were never harvested because there was no corn there to harvest. It completely dried up because of the drought. So we produced this type of yield increase and that type of a quality increase in drought conditions. How does that work? How does that happen? And how is it possible for the plant to get enough nutrition later on during the fruit fill period to still get that type of fruit quality even when there isn't adequate moisture and there isn't enough moisture in the soil? What we observed in this farm and what we've now observed in other farms since then is that it's actually possible by working with soil biology to some degree drought-proof a crop. You can make a crop a lot more resilient to water stress and drought stress, and there's a lot of discussion that goes into what the mechanisms are behind this, but at its very simplest, soil biology has the capacity to, so when we pick up a handful of soil that in our hands feels completely dry, like it's completely dried out, depending on soil type, sand, silt, clay, and so forth, there's usually anywhere between 50 and 55% moisture still left in that soil. But that is moisture that the plant roots can't access because the surface tension of the water attached to those soil particles is too high. So the plant roots can't get it, but bacteria can, and fungi can. So when you have plants and are growing a crop with really aggressive biology in the root system, the biology can actually access water and nutrients from really dry soils and make them available to plants that plant roots cannot get by themselves. So that can be one of the key factors to increasing water resilience in a crop. But the other really significant difference on this operation was an application that we had done in the spring of Rejuvenate and Spectrum to give us better soil porosity and soil tilth. There are a few of you that have used this. I know that Brad has used it, and David and Dennis can both speak to the effects that they had seen with Rejuvenate. Just a very brief background. Rejuvenate is not a microbial inoculant. It is a very powerful microbial stimulant that we developed years ago, and I originally developed it as a residue digester to put on corn stubble, particularly GMO corn stubble that did not degrade, sometimes where we have 3, 4, 5 years of residue or more sitting on the soil surface. We wanted something strong enough and aggressive enough to rapidly digest that residue without oxidizing it into the atmosphere as CO2. So we didn't want to use nitrogen. We wanted to use a biostimulant to digest all this crop residue. That was the original intention behind the Rejuvenate. There were several very unexpected side effects and side benefits from the Rejuvenate, one of which was that we got amazing soil porosity and soil structure and really good water infiltration. So there was one other key difference on this farm, which was that, again, it's been a while since I looked at this. I used to know this story by heart, but I want to say the beginning of May, they had about 2 or 2.5 inches of rainfall. That came very quickly.
3 inches in an hour.
It was 3 inches in an hour. So they had a dump of rain very quickly. And this is a picture of that farm and that soil within, what, a day or so after the rainfall?
No, those pictures were taken
Hours after the rainfall?
just, literally right after.
So where's all the water? The water all disappeared. It soaked into the field, soaked into the soil. This is the field directly across the road. So that field across the road that ended up later looking like a pineapple field lost all of its moisture. It all ran off the surface. And on this field, it all soaked into the soil profile. That was another critical part of the success that we had later on in the growing season, because that moisture then stayed there throughout the fruit fill period. So this is an example of soil aggregation, soil porosity. This was an oat plant that had grown as a weed. This is actually in a bean field that was right beside the corn field, but they were both treated the same with Rejuvenate and Spectrum. And the farmer who was on this farm has been running this farm for 30 years. When we pulled out this oat plant, just pulled it out of the ground, she looked at it. She said that in my 30 years of farming on this farm, I have never once in my life seen that. These are, when you look at this root structure, we have all this aggregation. You don't have any roots that are showing up as roots by themselves. They're completely clumped, surrounded, and clustered with aggregated particles from the soil profile because of the very strong bacterial community. This is another application of Rejuvenate we did in the fall, residue digestion on a farm. On the right, you can't really see this very well, but on the treated side, stalks on the right, they were decomposing very quickly, and we found earthworms in every single stem when the farmer said he hadn't seen earthworms in years. This next piece that I want to touch on briefly is that as soil health changes, weed intensity also changes. We understand that an alfalfa plant has very different soil requirements from a tomato plant, which is very different from a blueberry plant, which is very different from a corn plant. Every plant has its own specific nutritional profile that it does better in, and the same concept also holds true for these plants that we call weeds. And it is possible to adapt, to develop a soil's profile, both from it's very important, this is from many people have talked about this in the past, but they focus specifically on the mineral balance. Oh, you have this plant is an indicator of low calcium, that plant is an indicator of low sulfur, this plant is an indicator of excessive potassium. They focus purely on the mineral piece, but they're really missing a substantial piece, which is that of biology, because every one of these weed plants also has a symbiotic relationship with a specific group of microbes. So when you shift the soil biology and you shift the soil's mineral profile, you can actually develop soil that enhances a crop and suppresses weeds. I'm not saying it's going to eliminate weeds. I'm not saying that you're never going to have those weeds again, but what will happen is when diseases show up and when insects show up, they go to the unhealthy plants first. So if you can get to the point, you can actually measure this. A very simple and crude measurement is just simply measuring the Brix reading. You have, as long as the Brix reading on the crop is lower than the Brix reading on the weeds, the diseases and insects will go to the crop first. The moment that flips, and now your crop has a high Brix reading, and the weeds have a low Brix reading, the plants and diseases will go to the weeds first. This is a ton of fun. It's a ton of fun to see insects and diseases go to weeds. This is actually red root pigweed, which is a type of amaranth, on the farm that I grew up on in northeast Ohio. This is the middle of a tomato crop. This is more symptoms. I'm not even exactly sure what this disease is, or what it's called. But what I do know from experience is that these red root pigweed are never going to produce seed. They're going to die in about another 10 to 14 days. They're done. They're history. This is lamb's quarter infested with aphids. And this has a particularly interesting story because this was also on our home farm, where these lamb's quarter plants were growing was right at the intersection of three fields. So on one field, one section was tomatoes, one section was green beans, and the third section was a variety of fresh market greens crops. So it was salad greens, lettuce, arugula, mesclun mix, just a variety of different salad greens. And the salad greens and the green beans are extremely susceptible to aphids. Tomatoes not so much. But these other two crops are extremely susceptible to aphids. And there were no aphids in the salad greens, there's no aphids in the lettuce, there's no aphids in the green beans, and the Lamb's Quarter, right at the intersection of these fields, is loaded with aphids. Tell you what, that's a lot of fun. It's a lot of fun. This was a farm, this is not organically certified, but no pesticides have been used in this farm, no herbicides or anything for a period of about 8 years, I think, in Pennsylvania. This farm had severe problems with Canadian thistles, and they cultivated once. They got most of the Canadian thistles out except for what was right in the row. They weren't able to get good control. And they called us in to come look at it a couple of weeks later because all the Canadian thistle was dying in the row. So we actually pulled a bunch of samples, we sent them to a lab, and they were not able to identify any specific disease such as fusarium or anything like that that might be killing it. But these plants were covered with a white mold-like fungus. You can see a little bit of it in these photos on the outside edges of some of the leaves. But the Canada thistles in the cornfield completely died. We don't know why. We don't know exactly what we did that produced that effect, but we've now seen this on a number of different farms as well. So, now the question becomes, how do you do this? How do you actually make it happen? There's one other chart I wish I would have the time to go into, but if you remember the plant health pyramid, level 1 of plant health is photosynthesis. And when we talk about the idea of plants building organic matter while we are growing a crop, it is based on all of this is based on one simple foundational idea. Fact, I should say, not an idea, but an actual fact. Most of the plants, what we have come to accept as normal, corn crops out in the cornfield, all these plants are photosynthesizing at about 15 to 20% of their inherent genetic capacity. You think about that for a moment. That means that every square centimeter of leaf surface is only photosynthesizing 15 to 20%, producing 15 to 20% of the sugars that it could be producing in every 24-hour photo period. That is your yield. That's plant biomass. That's fruit fill. That's where everything is coming from. So, if you think about what that means, if it's 15 to 20%, let's just say you increase it from 15% to 60%. That means you've just quadrupled the sugar production in every 24-hour photo period. Now, where does that additional sugar go? If you increase sugar production by a factor of 4x, 3 to 4x, that sugar is, you'll get some larger plant biomass, you're going to get larger fruit yields, but you're not going to get a 4x increase in yield on corn or almost any crop. That's not a realistic expectation. What will end up happening with that sugar is that most of it goes down to the root system and out through the roots as root exudates. So, think of it this way. We'll use the corn plant as an example. From the moment the corn seed is planted until the crop is finally harvested, that plant's total sugar production is a total aggregate of 100%. That 100% over that plant's entire lifetime is going to be divided into 4 almost exactly equal pieces. 25% gets used to build the plant biomass above the soil surface, and 25% goes into the grain. Below the soil, you have 25% that goes into root biomass, and 25% goes out through the roots as root exudates. That is the way the plant will partition sugars over the course of its entire life, and obviously these divisions happen differently at different stages of development. But that division that I just described for you, 25, 25, 25, 25, 50% above the soil, 50% below the soil, that only happens based on the research that we have done and the experience that we've had in the field. That division only happens when the plant crosses the threshold of about 60% photosynthetic efficiency. In other words, most growers and most farmers never ever see this. You very seldom see plants that are at that level of photosynthesis. If they're not at that level, the ratios change. So the 100% of sugar production shrinks down substantially. And as it shrinks down, that means that you're still going to have an equivalent amount of plant biomass. So now instead of 25% in plant biomass, you might have 35% in plant biomass, and you might have 30% in grain. So now you have 65% above the soil profile, which means that you're only going to have 35% below the soil profile. That is the difference between healthy plants and unhealthy plants, and that is why unhealthy plants actually remove organic matter from the soil, whereas really healthy plants build organic matter in the soil. That's the fundamental difference. Again, there's a lot more science behind that I would love to talk about, but the point of this discussion is simply to say that everything starts with photosynthesis, and our entire nutritional system, our entire management protocol is based on one idea. You do everything in your capacity to increase that plant's photosynthesis. That's it. You just focus on that like a laser. You get that number from 15% efficiency to 60% efficiency or greater, and all the rest of this takes care of itself. The reality is, I can stand up here and I can talk about protein synthesis versus proteolysis, immune pathways, and microbiology, and I can make it sound all really complicated and really complex, and make it sound really sophisticated. But the reality is that on a practical level, it is really, really simple. It's really simple. Increase photosynthesis and get out of the way. Get out of the way. The reality is that if we can do that one thing, then everything else just flows like a cascade from that one thing, and it all takes care of itself. So I wanted to use this as a quick example. This is alfalfa production again in Pennsylvania. This is a farm where we had been working with this farmer for a couple of years. He bought a new farm, and on this new farm there was a fairly large planting of alfalfa, a second-year alfalfa, and there was a good population, a good stand, but the alfalfa did not look well at all. The soil was in pretty poor condition. He pulled soil analysis, and we made recommendations. He had the capacity and the ability and the desire to do a pretty complex mixture of, he used compost, humus compost, gypsum, rock phosphate. I think it was those three products that he combined and applied them all as a combination. So all of the alfalfa fields, 100% got the dry soil amendment. It got everything. And then he split his main field into three sections. One section, he put on no foliar applications at all. The second section, he put on one foliar application 7 days after the first cutting. And the third section, he put on two foliar applications, one 7 days after the first cutting, and the second 7 days after the second cutting. So that must be pretty sweet after lunch. So these are a couple of pictures that were taken from the third cutting. So these leaves were taken from the same location on the plant. The leaf on the left is from a plant that had no foliars. The leaf on the right is from a plant that had two foliars. So they're opposite ends of the spectrum.
Reverse that.
Oh, yeah, sorry. The leaf that's closest to me had two foliars. So if you look at this, there's obvious differences in leaf shape, in leaf size, in leaf color. And you look at these two leaves and say, well, yeah, what's that? Those are two leaves. You can fudge that, right? Well, this is what the entire plants look like. So left is no foliar, center is single foliar, right is two foliars. So what this meant in terms of yield was, interestingly enough, the plants, just the third cutting, the no foliar was a 3/4 ton per acre, single foliar was 1 ton per acre, two foliars was 1 1/2 tons per acre, double of the no foliar. So when you look at this, it's a substantial yield difference, and there's other differences in terms of feed value and quality as well that they notice, very substantial differences. But you look at the yield difference and you ask the question, okay, this all had the same soil application, all had the same compost, gypsum, everything else applied to the soil was identical. The only difference is the foliar sprays. How is it possible for a foliar spray of a few pints or quarts per acre of product to produce that type of result? And the key is that, and this is, as you become more familiar with advancing eco-agriculture and the work that we do, you will find very quickly that we are very strong advocates of foliar applications of nutrients. Why? Because years ago, when I was on our own farm and working with other farms to try to help them produce disease and insect-resistant crops, I was constantly asked the question, okay, how can we hack the system? What is the least amount of product that we can put in to get the greatest possible response? And the answer to that question is without fail, almost always foliar applications. Why? Because when you use a foliar application, you harness that plant's photosynthetic engine. You are harnessing an engine where you can put on a few grams or ounces of active ingredient per acre, a few ounces of manganese per acre, and you can turn that photosynthetic engine to go from 100 RPM to 1,000 RPM. Very quickly, you can produce a lot more horsepower that is completely disproportionate to the amount of product that you put in. So what this means for plant health, vigor, what it means for organic matter production. Let's go back to organic matter production, to our corn example. Corn is one of the best crops with which to build organic matter because it is such an efficient photosynthesizer. So if you, let's say you put on three foliar applications in the course of a growing season, and you spend $70 an acre for foliar applications on corn, and you get a yield response from that. The yield response is large enough that it makes a very strong ROI, as what Brad has been experiencing and other growers have been experiencing. But what I'm so excited about, what I'm so passionate about, is not just that we got a strong ROI, but with that $70 per acre application, we completely shifted that corn's sugar profile and where it moved sugars in the system. So Brad gained 1.2% organic matter in 2 years with $70 per acre foliar applications or less. How much compost can you buy for $140? How much organic matter can you build with $140? And you cannot afford to buy enough compost or to grow enough cover crops or to put on enough humic acids to build organic matter like that. There is nothing that is as efficient and as effective as foliar sprays in building soil health. And I know that it's the exact opposite of everything that we have been told for a very long time. So what I'm so excited about with this alfalfa, you look at this, you double the yield with 2 foliar sprays. But that's only half the story. Not only do you double the yield, but you produce a lot of sugars in the root system, in the soil profile, that was now better able to access the compost and the nutrients that were applied early on. And that's why we got a much bigger yield response with 2 foliars than we did with no foliar application. All right. David, this is for you.
Okay. This is a dairy farmer in Ohio who was doing a seed corn trial, and he was a strong, he's a loyal customer of ours, but the person who provided the seed corn also had a starter that he wanted him to use on part of it. So he, this is the different corn trials. You see the dark green rows was a planter of the same corn. So it was 607. I forget the number of the corn, but all the dark green strips were the same variety of corn. And then there were various trials in there. Here he used the AEA row starter, and then he sprayed Rejuvenate and Spectrum on that portion of the field, which is where that's where the trial ended. And And then he, out of curiosity, sprayed an X of Rejuvenate, as is shown there on the diagram. And when the yield results came back, which when they did the yield tests, this is an Amish farmer, so he doesn't have the luxury of combines and yield monitors. So they went out and they hand-picked 4 rows, 87 feet in from the edge, and they weighed it and did moisture analysis and so forth. And so if you look at the yields, you can see that we had 179, 186, 186, and then where that line drops is not in the X, it dropped down to 154, 153, and then it back up where it had the double is 218 and 207. So a very, very powerful testimony of what biology does. It's the only difference was the biology. And that was the yield difference you had, which is what we saw. It's just in a different format.
What happens inside, this is kind of a description of the exchange that happens between plants and soil biology. The first step that happens is you have plants that have full capacity photosynthesis. And what this means is you've crossed the 60% threshold of 60% efficiency. Sugar production has gone way up. So now, that plant starts sending a lot of sugars out through the roots as root exudates. When that happens, you get lots of sugar in the soil, you get very aggressive bacterial growth. So the bacterial population just explodes. You get lots of bacteria. Now, bacteria start consuming all this sugar, and if you remember how I described sugar this morning, sugar in its simplest form of glucose is simply C6H12O6, carbon, hydrogen, and oxygen. Why is that important? I just wanted to point out that there is no calcium, no magnesium, no phosphorus, no potassium, no zinc, manganese, copper, boron in sugar. So it's not there. So the plant is sending out sugar. Bacteria begins feeding on this sugar, but the bacteria also need minerals to form their own bodies, to form their own cells. So they begin extracting minerals from the soil mineral matrix and use them to build their own cells. And then, as this bacterial population cycles, the minerals that are contained within their bodies, the nutrients contained within their bodies, are released into the soil in a form that plants can now absorb and can utilize. This process, the third step on the diagram, is called mineralization. Bacterial digestion is called a mineralization because it releases minerals into the soil profile. Then, the next step is really fascinating. Plants now begin absorbing a lot of their nutrition in the form of these microbial metabolites. And this is important. There are 2 frameworks of thinking for thinking about how plants absorb nutrients. One of them maintains that plants can only absorb nutrients in the form of simple ions, calcium ions, potassium ions, nitrate ions, and so forth, which is fundamentally a hydroponic model. Plants do have the capacity to do this. That's how hydroponics work. The second maintains that plants also have the capacity to absorb microbial metabolites, amino acids, such as glycine and methionine and cysteine and leucine from the soil profile, and also organic acids, such as carbonic acid, acetic acid, citric acid. And the interesting part about all of these amino acids and all these organic acids is that they are all chelation agents. And they chelate and hold minerals from the soil profile. So now these plants are absorbing all these organic acids and amino acids bonded with minerals. And this is an extremely efficient way of absorbing nutrients. Why is it efficient? Let me just talk about nitrogen for an example, because it's all the way on one end of the spectrum. Plants can absorb nitrogen from the soil profile basically in four forms. As amino acids, which is the most complex form, as urea, as ammonium, or as nitrate, or as ammonium and as nitrate. So nitrate, ammonium, urea, and amino acids. When a corn plant absorbs 80% of its total nitrogen requirement in the form of nitrate, it requires 12% of its photosynthetic energy just to convert nitrate to amino acids. So think about this. Every 24 hours, all the sugar that that plant produced in 24 hours, it's sucking up 12% of it just to convert nitrates. That's a tremendous energy drain on that plant. Think of it this way. You want to build a tractor. You have the machine shop, and you have the right tools and the equipment that if you wanted to, you would have the capacity to machine every single part and build your own tractor from nothing except stock. No. You could do that if you wanted to. Or you also have the option of purchasing parts that have already been manufactured and just assembling your tractor from scratch from already manufactured parts. Which is going to take you the least amount of energy? The pre-manufactured parts. Of course, it's going to take a way less energy. The same idea holds true of plants as well. When they are absorbing amino acids and absorbing microbial metabolites, it's the equivalent for them of absorbing pre-manufactured parts. And they become very efficient. So when they become very efficient, now, if you go back to the plant health pyramid, they now get to level 3 of the plant health pyramid where they have a surplus of energy, and they store this surplus energy in the form of lipids, plant fats and oils. They become very energy efficient. Now, this is where the fun starts happening. When you have a plant that is producing high levels of oils, high levels of lipids, it will now begin also transferring these lipids out through the roots as root exudates. But guess what? Bacteria can digest oils. That's why in our culture, I don't know, perhaps not so much in yours, but in our culture where I grew up, people would many times preserve meat by storing it in fat, because bacteria can't digest fat. But fungi can. So now, instead of bacterial digestion, you get fungal digestion. And fungal digestion is very different from bacterial digestion in that when fungi ingest something and they consume it, they simply digest it and process it over and over and over and over again. They do not release it back into the soil environment until it reaches a point at which it can be digested no further. That point, that compound, that substrate that is now released back into the soil environment are called humic substances, humic acids. These are compounds that have a half-life in the soil in terms of hundreds of years. They are very stable organic matter that does not degrade and does not decompose. So, this is a very interesting point here. I said that fungi, and by the way, this process, the last step in the process, this fungal digestive process is called humification. This is how you build soil organic matter. You grow plants healthy enough that they're producing oils and sending oils out through the root system, and you build soil organic matter while you are growing a crop. Now, I said that fungi will digest something until it reaches a point at which it can be digested no further. What do you think establishes the cutoff point? When does the humic substances reach the point where it can't be digested anymore? When it reaches a concentration of lipophilic acid, of lipids, of 40%, from 38 to 42%. 40%. So, what does that mean? What I just said, if you follow this through all the way, is that the amount of organic matter that you build from a crop has nothing to do with how much carbon and how much crop biomass is in that crop. Instead, it has everything to do with how much fat is in that crop. Let's say that you have 2 fields of cover crops. I'm making it up. Let's say you have 2 fields with an oats cover crop. One field has 2%. Both fields have 5,000 pounds of plant biomass per acre. One field has 2% fat content. One field has 6% fat content. The field that has 6% fat content will produce 3 times more stable organic matter than the field that has 2% fat content, even though they have the exact same amount of plant biomass. So that is how you build soil organic matter, is you have to grow plants. There's a reason the Bible talks about the fat of the land. You ever stop to think about that? The fat of the land. So when you begin sequestering oils and lipids in the soil profile, and you get very strong fungal digestion, you can build organic matter while you're growing a corn crop. And as Brad experienced, and I will absolutely say that Brad's was an exceptional experience. We often do not see jumps that fast, that rapidly. But 1.2% gain in organic matter in 2 years on organic corn, that's something worth writing home about. That's pretty exceptional. And that is what is possible. It is possible for us to regenerate soil health while we are growing a crop. Okay, enough about that. Let's talk about how to do this, and more importantly, how to do this in Kansas. David, I think you should perhaps get up here as well. We've looked around, we've talked with Brad, we've talked with Ashley, we've talked with Roger, we've talked with other farmers and growers in the area to try to get a sense and a feel for what is happening, what are the crop systems, what do the rotations look like. And so in this next little section, what we'd like to talk about is what are the problems that we see and how do we think things need to be done differently in order to resolve some of the challenges that we see today. And before I jump into that, I would like to say that we, so far in our discussion today, with the exceptions of talking a bit about rejuvenate and spectrum, we have not talked about products. And this is very common for us. We talk a lot about the information, the science, and stuff that's going on, and we don't talk about the products and what needs to happen. And we're changing that deliberately. We want to talk about some specific pieces that need to happen. Why? Because we believe that we will be able to really help bring some insights and bring some ideas about how to change and how to bring some improvements to the agriculture that is happening here. We're very serious about it. We're very passionate about it. We believe that we can help you make a difference. We want to make a difference. At the same time, all of us on our team, David and I and the rest of our team, we are very busy. We have a lot on our plates. We have a lot of demands on our time. And we want to come out here and do it. And we want to do it properly. We want to do it well. We are not satisfied to do it halfway. Either we're going to do it right or we're not going to do it. We don't have the time to waste messing around and doing it half-assed. So, David has set the goal that we want to come out here and work with a group of growers, and at a minimum, we want a commitment from you collectively and the larger community of farmers to run 2 years of trials on at least 30 circles. And with that commitment, we will put our full energy and resources behind to make absolutely sure that we get the types of results that we are looking for. Because as I described earlier this morning, we don't pretend to have all the answers. We don't pretend to have it all figured out because we haven't and we don't know everything. We're not approaching it from, it's also from a very practical perspective. Given the fact that we're a small company, we're growing very quickly, we have lots of demands on our time, we can't afford to send people out here on a constant basis to get something started on a small basis. We need some level of skill in order to make it worthwhile for us. We don't think that what we're asking for is unreasonable or unrealistic, and quite frankly, we believe we're going to be able to make anybody who's a participant in that a lot of money pretty quickly. So, we want to talk about, for a few minutes, about specifically some of the things that we see. I want to go back first to the point, sorry, I'm just running away. Do you have anything else to add? When I was talking about sap analysis, talking about the nutrient interactions diagram, one of the points that I made very intensely is that many of the problems that farmers are experiencing are created by the excesses of the products that they are applying. And based on what we've observed so far, we absolutely believe that to be true in the current corn. And for the context of this conversation, so far today, we've been focused heavily on corn. Obviously, corn and soybeans go similar to some degree, but I'm focusing on corn in this specific conversation. We believe that one of the major challenges that we are seeing, a major source of the problems for spider mites and everything else, is the anhydrous ammonia application in the fall. This is a big problem. I could talk about anhydrous ammonia for 15 minutes, but by the time I got done, you might run me out of the county. out of the state. But anhydrous ammonia really does a number on soil biology, has a very negative impact on the soil profile, produces a lot of compaction, really kills off a lot of soil biology. But that isn't the biggest problem. The biggest problem is that the following year, remember, what is one of the strongest infrared signal pumps and amplifiers is ammonia. And whatever ammonium we have remaining in the system, in the soil system and absorbed by the crop, is going to serve as a strong infrared signal pump and serve as a calling card to call in the spider mites and the insects and everything else that we wanted to avoid. So, we do not believe that there is any value in adding nitrogen 180 days before the crop needs it. So what we want to do instead is, for nitrogen management specifically, is to irrigate and or side dress on dry land as appropriate, to apply nitrogen in the crop season as needed based on sap analysis. And what you will almost invariably discover is that the amount that we recommend, once we have sap analysis, once we have hard data about what the plant is actually needing, our recommendations are likely to be a lot less than what you guys are applying today. What we have seen on other operations is we are consistently, once we start using sap analysis and actually measuring what is needed, we're consistently reducing applications anywhere from 30 to 50%, in a few exceptional cases even more than that. And so a big part of that is obviously applying it later, applying it when the plant needs it. This is going to be one of the first pieces and the most important pieces for insect management. If I can tell you guys right now, if you're not willing to not do the anhydrous application in the fall, then anything else that we might do, foliar application, sap analysis, so forth, are going to have minimal impact, because this is the foundation for a lot of the disease and pest problems that are happening. So,
on that nitrogen point of reducing nitrogen, we might just throw in and talk about how much nitrogen we have in the atmosphere and what, like 3 minutes, whatever.
We only have 7 minutes left.
Bottom line is, the atmosphere has 78% nitrogen, and if we have the proper bacteria and the carbon in the soil, we can harness that nitrogen. A corn plant can harness that nitrogen. It doesn't have to be a legume.
Yeah, this is actually something, there are now a few patented products being developed around this, but this is something that's been also knowledge that's been around for a long time. There are all types of microbial inoculants, being azotobacter and others, that fix nitrogen out of the air in the absence of legumes. They do not need legumes to fix nitrogen. So what you need for those bacteria, however, is you need to have the right environment for them. You're not going to have the right environment with anhydrous ammonia applications. You're not going to have the right environment for those types of bacteria to thrive if you can't even get legumes to nodulate. If you can't get legumes to nodulate, those bacteria aren't going to thrive either. So, and again, are we saying that those bacteria are going to supply a lot of nitrogen the first year, the second year? We don't know. Maybe they will, maybe they won't. But sap analysis will tell us. We don't have to guess. It's not a guessing game anymore. The next piece that we would like to see is replacing that nitrogen application in the fall with a fall strip-till application of Rejuvenate and Spectrum Extra, and 5 units of nitrogen as either ammonium sulfate or a combination of N32 and thiosol. And what we are after here is actually, we're after the sulfur more than we are after the nitrogen. Because, why is this? With Rejuvenate and Spectrum, we want a very strong biological push in the fall, but a major part of building organic matter is having enough sulfur in the system. So, what are you laughing about, Roger? Oh. Would it be the first time? So, sulfur is required for maintaining organic matter in the soil profile, and this is how it works. 1 part of sulfur will stabilize and hold 10 parts of nitrogen. So that's that 10 to 1 nitrogen to sulfur ratio that many people talk about. Then, those 10 parts of sulfur will hold and stabilize 300 parts of carbon. So stable carbon to nitrogen ratio is 30 to 1. So 1 part sulfur, 10 parts nitrogen, 300 parts carbon. So another way to think about this is that the soil digestive process that will digest down and break down carbon, the carbon will oxidize into the atmosphere in the form of carbon dioxide down to the lowest common denominator. And often sulfur is the lowest common denominator. So if you have higher levels of sulfur, you can hold more and build more soil organic matter. So what we want with this application in the fall is we want to make sure that we have a small amount of sulfur in the system with the Rejuvenate and the Spectrum Extra. And then, yeah.
I think number of farms, wild acres, that had 50 and maybe 90 years. With quit using it, I guess that first year was almost like a shop pit for it. So this application helped that, right?
It does help that. You have to be really careful, and this is a lot of reasons why we ask for a 2-year commitment, because the first year is without question a transition year, because soil that has been acclimated to those applications of anhydrous ammonia is, for lack of a better term, it's like a drug addict. It is addicted to that fix, that flush of highly soluble nitrogen, and if that is not present, then you have to replace that with other things. So with the Rejuvenate and Spectrum Extra application, you can recover from a lot of that over the winter months, and you can eliminate a lot of that transition period, but you have to manage it correctly, because it would be inconceivable to think of going from anhydrous ammonia applications in the fall to cutting nitrogen 50% the first year. That is a recipe for disaster. That's not going to happen. We don't expect that to happen. We're going to have to transition. We're going to have to figure it out and see what makes sense. Yes, David? Anything else? No? All right. The next piece is that in the spring, we will put together a customized planter solution for in-planter, in-furrow, either preferably on the 2x2, can also be on the seed, depending on what growers are doing. This would be a liquid application, and this application is going to be a combination of biologicals and nutrients, and it is going to be customized to each farm based on, if needed, it might not always be needed, but where needed, as needed, and it is specifically going to be designed to provide all the trace mineral enzyme cofactors that plant needs for very strong reproduction, those early phases, remember that 9 to 12 day window after germination. Doesn't make sense to put a foliar on then, so we want that planter solution to have all the trace minerals needed for strong reproduction, strong ear embryo set early on, and to produce a very stress-resilient plant in the early stages. And then we want to work with sap analysis. We will start with sap analysis at about V4 to V5. And, yep.
What do you base that planter?
That will be based on soil analysis. Soil analysis, and if we have any historicals, looking also at historical tissue analysis that you might have if you have any. And then we'll start with sap analysis at about V4 to V5 on corn, and then we will make recommendations for specific customized foliars or irrigation applications. And these applications, the customized foliars, corn, beans, we would expect 2 to 3 applications, possibly 4 at most. And we want to design these, we will be designing these foliar applications, these irrigation applications, with 2 objectives in mind. One, as I described earlier, we want to increase photosynthesis as much as we can. That's the one objective. And the second objective is putting in any specific nutrients that the plants might gain from, or might give them an advantage in producing resistance to spider mites, producing resistance to these specific diseases. Those are going to be the 2 objectives that we will be using to formulate these foliar applications. And then, based on the sample analysis following those foliar applications, looking at all of this, we are looking for a commitment from you, and also, in exchange, we are making a commitment that all the recommendations that we make in aggregate, the fall application, the planter solution, the foliar applications, everything together, but in addition to what else you might be buying in terms of liquid nitrogen, pesticide, pesticide budget, and so forth, in sum total, we will remain plus minus 10% of whatever your current budget is today. So we're not going to go out and spend a lot of money. We're not going to do anything radical or crazy, and it's very possible, we can't stand here and predict this because we don't know, but it's very possible, as with what Brad experienced, we may be able to produce these types of results for a very small amount of money, $50 to $70 per acre. But we can't claim that and say that we're going to do that right now without knowing what it's actually going to look like.
So in that, we don't work with growers in the context of this is what you need to do and walk away. It's more of a partnership where we say, all right, well, what have you done? Where are you going? And we work together, and the farmer says, well, but Brad will say, but David, what about this? And it's like, oh, yeah, that makes sense. So we work together. It's very much a team where we're not just here to give you a recipe to put on here, but it's much rather to help you understand why we're doing what we're doing. You'd be able to run with a regenerative program from here.
Yeah. Our company, as I described initially, we started as a consulting company. We did not start as a product company. The products actually, after doing consulting work, 2006 and 7 and 8, 3 consecutive growing seasons, by December of 2008, I was becoming very frustrated with the lack of performance that we were getting from liquid products in the marketplace. And I spoke at a national conference in December of that year. And I publicly made the comment, I said, I could make better products than most of what are available in the marketplace today. And there were 2 people in the audience who came up to me afterwards and said, we believe you're right, and we'd like to help you get started. So they invested some money in advancing eco-agriculture and helped me get started. And we did a lot of product testing and R&D in 2009, 10, and 11 before we first started putting products in the marketplace in 2012. And so as a result of that consulting heritage, we still take a very in-depth consulting approach to working with farms. I would say perhaps much more so than you may have experienced otherwise. We are very much on call, on hand. As David said, it's been one of the weaknesses that people have ascribed to us as a company, that we don't talk about products, we don't promote products enough. Instead, we're giving away a lot of free information. Well, we believe that information can help a lot of people. We're very passionate about that. So we share that information freely, readily with any grower who wants to call us and ask. We have those conversations all the time.
How much on a day-to-day or week-to-week basis, obviously this is a little more intense than what I'm used to. Like as far as how much more work can I expect to do, or
I would say that'd be a good question for Brett.
Can you imagine a different type of analysis on corn plant versus the not talking about? You want to talk about it? It only takes about 5 to 10 minutes to do that stand on corn, so they're not taking give it while getting corn.
As far as number of applications, you probably don't have more applications than you do with pesticide applications. I don't, as a whole, you're maybe involved more in the crop per se. You're paying attention and making decisions in a different manner, but I don't think you're going to be spending a whole lot more time, physically doing what you're doing.
A big question for Ashley. Did you experience spending any more time really with him?
I did, but it's my first year. I could have done more, really. But maybe I should have done more.
we have to recognize as well that what we're talking about is, in some regards, it's almost a fundamentally different way of thinking about pests, fundamental different way of thinking about diseases and how to manage crops. And there's a learning curve that is associated with that. The first year or 2 years, I can see where it would be possible to spend a bit more time, but long term, I think we could speak to many AEA, long-term AEA customers who say that they spend perhaps, if anything, less time now than they did, because they've learned it and it's become second nature to them.